4 week. And finally, we are going to have our last class, which is only left, including today, we only have 5. And we are going to cover 16 of 15, 16, 17, everything here. And let me coming back to lecture this sections, and you can see I also have created all the practice quizzes on our discussion, not discussion, web courses. We have 15, 16, 17 or ever created. But once we cover all the materials, you are simply get all the informations or the quizzes. And today we will complete the talk of lecture 14, and you have seen 49 different questions to touch on the lecture 14. So simply go practice on that. But another update I want to give you is about final. So previously you have heard me talk about, you are going to have 50 different questions, 50 different questions. I have think, is that something I truly want to test you on? Do I need to really suffer you for like taking different like 50 questions? Is that something that truly reflects to your performance or not, your learning or not? So I'm coming up with the answer, the concrete answer is no. So 50 question is not something that I want you to do in the final, especially you are like very stressed out. But whatever you are doing here, you should also be well prepared because I have all the questions being published right here. But what I'm going to do is to reduce the amount of questions to 19. 19, 19 different questions, all coming back from your lecture 9 to lecture 17, and including a one applicational questions from your homework 4. If you truly understand your homework 4, you should be able to do that. And the format will be exactly the same as our lecture 10's practice quiz. It will worth 10 points. If you missed it, you missed. Okay? So that is the thing I truly want you to understand. Okay? If you can do absolutely correct in homework 4, you should be able to complete this question without any doubt. All right? Then coming back to your the entire formatting actually created the final exam, but let me just simply demonstrate it to you. 19 different questions, 100 points, 170 minutes for the entire exam, but you have to come early. You have to come on time, all right? What you can do is you have open notes, one sheet of paper for the note, front and back. Whether you printed it, whether you're doing something, it doesn't really matter to me. But what you are going to do is for the attendance, you have to, I'm still considering whether my TA is able to access to the UCF here or not, as I will be gone during the final exam day as my baby get born. Yeah, so unfortunately, that's not something that I can present in person, but you got your TAs standing right behind that door. And before you're leaving the door, the room, you have to show them that you have complete this final exam. Show the evidence and handing your note and a scratch paper to them. That's the only thing you're going to have. And so I will have them to come to the class to test out UCF here next week. So you will see your TA coming back here and having some UCF here to be like manipulated to record that day's attendance. If that's not something that works by the system, like privileges, then we have to go back to the manual sign-up sheet. Okay, but if we got 100 different students sign up, it just could be a chaos. All right. But what is actually the format you are seeking? Is actually coming from the practice quizzes I give to you. It's just simply random choosing from the practice quizzes. If you practice, you got it 4 points. No surprise questions. If you do absolutely your work, your hard work on practicing, you should be able to get 100. Yes? You're just glad. Yeah, I'm glad too. So I have made my hard work for teaching this class. I'm giving you all the resources that have never been done before. That is my goal. I want to learn. Okay. Any other questions, comments, complaints, anything? What's that? What's that? You do you, okay? All right. So, truly, nothing? Okay. About homework 3, whether you receive some grade, you have any objections to your grade, you have to talk to me in person. Do not email your grader. They do not have authority to manipulate or modify your grade unless I have given explicit instruction to them to modify your grade. Okay? Do not talk to your grader and ask for any favors to modify the grade. You have to talk to me. Okay? But before talking to me, you should be reading the instruction again. Okay? So let's coming back to the lecture. Any comments? If not, let me continue. So my goal is to finish the lecturing before next week, actually. The entire slides and everything before next week, so that you could have a dedicated sessions for the reviews, or we can completely get rid of the Monday's class. You could have a more time for the review, or you can enjoy your holiday, actually. Okay. So now let's coming back to here. So last time we have talked about basically this slide, right? So this slide is basically representing all the states with what we have here for each processors or for each process. But we haven't specified what kind of actions it will perform from moving one state to another state. But here we are expanding that diagram to adding a more specific events, more specific actions that triggers each state transition. So when the process is created, it moves from a new to ready state. It is simply the scheduler dispatched to the CPU to make it running. So creation from new to ready queue and dispatch by the OS. If the CPU time slice expires, so simply the timer interrupt because simply causes it to moving back from the running state to ready state. So that's the timer kick in. When a process starts an I/O, if it's running here, it starts I/O operations, loading as SIO, simply moving that running state to waiting state, that waiting for the I/O. Since I/O, once the I/O finishes, the interrupt signal's completion simply bring back to the ready state. Okay, if the process finished successfully, let's say successfully, basically we have some kind of end of file and an EOP things being encountered in the program executions, they simply go to the end state. All right. Then if something were happened accidentally, simply we trap it to abandoned state. But what is the suspended state here? It could be something initiated by the OS. OS have something related to some say we have to allocate some resources, more resources. We have to make this process to wait a period of time. So we are going to suspend state. Simply stop it and resume it from the suspend state. Any question? Okay. So what we have here is a summarizations of main reasons that a process changes from one state to another. Just simply focus on the triggers of those transitions. Especially we are focusing on the running state to some kind of like ending state or abandoned state or some waiting state. So the current state is running everything is currently running. And if we are encountering the end of the program flag, we simply end it, go to the end state. So the interruption will be EOP. The EOP is action. And the running is if we're going to get into the abandoned state, so it means some trap happened. It's OV or MP or PI will be the trap we're talking about. Running, if we're going to running state again and starting an IO or any kind of IO operations, we'll simply block it or make it into the waiting state. But here is blocked state. So in the block state, and what is the interruption? It will be a system call or SIO. Okay, any question? Simply illustration. And giving you the table is not sufficient, but we have to understand in a diagram format. So this is a diagram we are having. So running to end, where the action is EOP. Running to abandon, it will be the trap. Running to the block will be system IO or system call. Then let's quickly recap what do we have learned about PCB. What are the PCB we're talking about? Come on. Anything? No? You forgot about PCB? Come on. Process control block. So it is what we have learned about why it is critical, why it is crucial for the process management. Every time a program is loaded into the memory to run, and the operating system creates a PCB specifically for that process. That's the idea we are having for the PCB. Essentially, the PCB acts as a process identity card containing all the critical information, such as, let's say, the current state, the unique identifier, and the IDs, and etc. That's the information that the operating system needs to manage their life cycle, each process life cycle, and the resources effectively. And what are the information we are talking about in the PCB is it will store all the details, what we have here, the list of them, the current state of the process, whether it's ready, running, waiting, or suspended. And it's also have is keeping track of a unique identifier. We could have the PID, which is process ID, which helps the OS to distinguish each process distinguishingly. So what is a current PID? Could be something that is related to the OS is working on that. And additionally, we have PCB records the process priority level, which it is something that we have to talk about. Then some process should have some priorities, such as IO allocations or some system allocations or system programs should be having a higher priority than your normal program. So that will making the operating system making like running smoothly. Then we have contents of some CPU registers that is register containing some instruction pointers known as PC and memory boundaries. What we have here, the base and the limit registers. If you still remember, we have a dedicated space for that, and just saying if it's something below that register, below that fence, we are getting into the memory protection area, which is prohibited by if you are in user mode. Then last thing is about the time limit, in which is a TI or timer. We are talking about hardware implementation. And IO status informations is basically whether the process is working on IO or not. So those all detailed information, the OS will smoothly switch the process in and out of executions, ensuring each process resume exactly where it left off. That is the idea. Then what we have here is basically a visual demonstration of reminds us the PCB structures. The PCB essentially is an operating system snapshot of a process at any given time. So it includes the pointer for managing the process, and identifiers such as PID or process name, and important like limited memory boundaries such as base and limited address, then critical areas of critical registers such as instruction pointer, which is also known as PC, program counter, and stack pointer and registers and state, which simply record whether it's running, ready, or dispatching, or suspended, or etc. That's the state we're talking about. Then we have the mode. Mode is basically indicating whether it's user mode or another word is for that is Supervisor mode, great. So supervisor mode. Lastly, we have the interrupt flags, which is represented in a PSW. All right. So now we shift our process to threads. Of course, in the previous slides, you also see some like threads control block, the TCB here. So we simply switch the process to threads, which we are going to introduce them in detail. What is the thread? We have to understand. Fundamentally, what is the thread? Anything? What is thread? Yes. What? You tell me. Whichever you understand, just say it. You don't know how to organize your word? Yeah, it's fine. Any other answers I may have? No? So we haven't touched on the thread, but what is your general understanding towards a thread? What's that? Who is speaking? Yeah. Anybody? No? You? Yes? A line of execution. Okay. Any other ideas? So you all agree on that? Yes? On that system, right? But it uses that one thread. Okay, lost the words. Fine. So what are we talking about here? The thread is often called a lightweight process, which is actual unit of execution inside a process. Okay, so lightweight process. So while a process provides some environment, is having its memory, its files, its resources, a thread represents a sequence of instructions being executed. So thinking a process as a team project, and each thread as a team member working on that same project, similar to your homework instruction. If you are working in a team for this entire class and you got instruction the same, you got all the information the same, and both of you each one of you could be working on independently on different pieces. For example, in homework 4, we got 3 different pieces. Your teammate could be working on Lex.C modifications or VM.C modifications. Your job could be only working on parser code.c for the modification. Okay? So all members share the same material, but each has its own workspace and task. The threads allow the work to happen concurrently, improving the efficiency and the responsiveness. That's the definition for that. Each thread has its own execution context, which is the operating system tracks is using by what we have called TCB, thread control block. So similar to our real life, you are working in a team. You got the same material, you got same instructions in the homework instructions, but each one of you working on a different laptop. Yeah, right? You could be working on the same laptop, but most likely you are working on your independent laptop, which is independent from the others. Okay, so the TCB, what do we have here? Yes? What's that? How many threads we need for a one program, which is unknown. It depends how many threads you need, how many workers you need for that project. You could decide, but normally we're talking about is one thread per program. Okay, normally we're talking about that. But the TCB, what we're talking about here is the most focus is the TCB, not the thread itself. Okay, the TCB. TCB is a more smaller version of PCB containing all just essentials for the CPU scheduling, We have program counter showing which instruction of the thread will execute next, the stack pointer, the CPU registers, such as storing the temporary computation data, and thread's current state could be running, could be ready, could be waiting. And since threads share the process address space, the PAS, and resources, and TCP is much lighter than the PCB, which makes the threads creation and switching much faster than the full processes. So in short, the TCP allows the OS to manage multiple threads within a simple process efficiently, keeping each thread's execution context distinct and while they sharing memory and system resources. That is the idea. So we have discussed in detail how a process is created that enters the systems. And the process creation typically begins with some like operating systems, either is when it boots or through a system call issued by a running process. So for example, if a user application might request a creation of another process to handle a specific task, for example, your web browser launches a separate process for each tab you are opening. And in these cases, the process that initiate the creation is called the parent, and the new one is being created is called the child. So when a process is created, the OS first simply places onto a new state that here the system simply allocates the necessary resources, creates the PCB, and sets the initial memory structure. After the setup, the new process transition from the new to ready state, as you can see right here. It simply joins the ready queue, waiting on its turn to run according to the OS scheduling policy. Essentially, it starts back of this queue and eventually moves forward to the front, where it will be dispatched onto the CPU for execution. This slide, what we have here is should be exactly the same you have visualized before. That's simply outlining the basic step involving the creation of a new process. We have the program sitting on the disk and loaded by the operating system, and the operating system simply goes to that memory to reserve the space for that program. And we have created PCB. That area is called PAS. Okay. Then coming back to here, what we have talked about PAS, well, exactly it is. So object file is what is sitting on the disk, and a memory is so operating system simply reserve a PAS, process address space, in the memory to make sure that the program running in that state rather than below or across some limitations. But what exactly we are creating inside this PAS is the PCB we are creating. So the PCB is holding all the informations. Now, coming to the review questions. What is text? What is text is holding in this area? Who is saying instructions? Great. Good on. Yes, instructions. Instruction of the program. Where it's coming from? From the object file. Which part? Which sections? You only have those information. Text from text. Good. So literally. And data. Data is coming from where? What? Data? Yeah, data. But we have BSS. What is BSS? BSS. Uninitialized data. Correct. But how is it distinct from the data itself? This data we're talking about. How is it different? Yes. One is initialized, uninitialized. Heap, of course, the heap, we're having a dedicated sections for that heap introduction, so don't worry about. Stack, all the information what we have talked about in activation record. So here is a slide that we are getting everything like integrated together. So we have The text is simply the instructions. X equal to 4 is the instructions. It could be lit4 and load to or store into something. That's two instructions. Data could be the constant or initialized data. What we have here is integer y is equal to 7. 7 is, so that is already be initialized. The global and static variables, which is uninitialized data, will be placed in the BSS. And heap is dynamic allocated variables will be using the malloc in C to reserve that space. And the stack is the things we are managing everything that's such as static link, dynamic return address, local variables, function parameters, and etc. Okay, and the return values. Then coming back to here, what we have to talk about, the BSS is what? So simply on this slide, we have the block started by the symbol. Okay, then that is the idea. We have the BSS, that's the interpretation. Then it's coming back to the stack. So we have understanding the stack for extensively from your homework 1. So we don't have any further introduction to the stack. Do I need to? The only thing you need to remember is that whenever we are having a list, so we're simply creating a temporary area in the stack, in the local variables. List of 6 means we have to create 6 different items consecutively in the stack area or activation record, or we call stack frame, in having different names. Stack frame is equal to activation record, all right? Then coming back to here, we are simply exploring the threads. So we are talking about threads. That is our main context of this lecture. So the threads could be coexist within a single process. That is the idea. Threads is a basic unit of a process and a multi-thread in a multi-thread programming and program. Each thread represents a separate unit of execution, while all the other threads share the same process address space, including the code, the global variables, the heap, and everything. Each thread must have its own stack. That is the idea. Each one of them have its own stack. This is because each thread maintains its own local variables, function calls, return addresses. In this diagram, as you can see here, we're simply having an illustration of each stack is having a one single thread. But to answer your question is, how many threads we're actually having in an actual program is running? It still depends on the programmers. Whether we are going to do things this way, we could have one single stack having one single thread to run it, or we can have an entirely single thread for running everything. That is exactly what virtual machine is doing. Your virtual machine is considering we are having one process. That process is only having one thread. That's it. But once we having multiple threads, it could be more complicating about context switching. Okay, so each thread having its own TCB, thread control block, which stores the CPU state when it's not running, and the multi-threading simply improves the efficiency by allowing the concurrent execution, but it also means all threads can access the shared data, requiring some synchronizations to avoid race condition. Okay. So coming back to the race condition, you have heard about this word. And I believe everybody here have already taken the security in computing class. No, it is not required for what? For this class, yes, but it is required in the mandatory class for computer science and IT, right? But whether you are going to take that or not. So for whoever have taken that class, you should be having a good understanding towards race condition. Can you explain? What? No, you cannot. Yes? Mm-hmm. Yeah, that's kind of idea that if it's, yeah. That is a great interpretation. That is a great. Just keep this idea in mind. So it will be introducing some unpredictability of behaviors, actions. So just simply keep this idea. What is happening? We will further examine this question in our lecture 17. Okay. So whether you understand risk condition, whether you understand deadlock or not, we will getting on that. So in lecture 17. So don't worry about it. Then coming back to our lecture, we have talked about avoiding risk conditions, but how is the TCB is working in practice? That is the idea we are illustrating here. So we're basically connecting all the understanding about the threading to how CPU interacts with them. And each thread has its own context, as we can see here. And we simply assume each stack has its own thread context. That's TCB. So stack T1 has its own context, TCB T1, stack T2, TCB T2, stack main has its TCB main. But what we are illustrating on this slide is current running function or current running thread is stack T2. And basically it is from the TCB T2. So the big assumption before what we are going to talk about is that the current running function. So every thread has been run, all the information is being saved to a TCB. And when we want to run a certain thread, simply we are going to load this information from the TCB and go to that CPU to have all the information ready for the execution. So PC directly go to that PC, load it to the PC, and the PC is indicating what is the exact instruction we are executing next. SP directly loading from this information, go to the SP and finding, okay, well, my current stack, the top of the stack is here. And the registers is basically loading from the registers. And lastly, the state is basically switching from the ready queue to executing or running state. Then coming back to here, simply this slide is illustrating when the CPU is idling, so nothing is being executed. So every information is being saved to its corresponding TCB area. That's the only thing you need to remember, nothing else. But once we come into this slide, is simply illustrating what happens if I'm going to have the stack T1 to introduce or to executing. Previously we have T2 is running. So T2 is interrupt by the OS. And further, those interrupted information is going to save to the TCB T2. T2 is having all the information saved, and then the OS will simply load the TCB T1 information back to the CPU and for the execution of this thread T1. Any question for that? That's what we call context switching. We are switching the context from T2 to T1, okay? Any other question that we have? No? Great. So this is the final diagram we could have is basically integrates the concept of the thread with the process executable format. On the left, you can see the ELF file. Simply when we want to create some runnable file, or we are going to run the program, we have to load the information correctly. The data goes to BSS and data, the code goes to the text code, and symbol table basically is allowing us to resolve those information being correctly or not. But once we having all the information loaded to the memory area, we simply create all the TCBs, and now everything can be running smoothly. And here you can see the picture is thread is T2 is running the CPU. Simply, previously we had T1 is running. We simply save all the information to the TCB T1 and load the information from T2 to successfully to resume context switch to T2 to make it running smoothly. That is the only idea you could have. So context switching is the key. The only idea I'm introducing here. Okay, anything? If you don't, let's continue to the next lecture. And if you are, before the lecture starts, I'm modifying the slides. Okay. So in this lecture, we'll simply transition to our discussion of heap. So previously, if you were in the class, so I have introduced the difference between the stack and heap. How much information do you still remember? What is heap? Yes. Arranging it virtually can simply virtually thinking it's a one piece of memory so that we can work on. But now we come into the actual implementation of the heap. So how is it different from my so how is working in a real life? Why is creating some fragments? Why is being like divided by different memory areas? What is happening right here? Okay, that is what we are addressing. So we want to take a very deep look or detailed look at the heap fits within the overall memory layout from a process using the diagram right here. And recall from earlier lectures that our process address space is divided into several segments. What we have here, a test segment, the data, the BSS, the heap, the stack. But in our diagram, the heap is represented as an array of memory words. So each box here will label as word corresponding to one memory location. So this array visually illustrating how the memory is managed dynamically at the runtime. So initially, the entire heap, once the OS is booting up, so the initial stage, or entire heap is free. We maintain a pointer, as you can see here, the pointer here is indicating as numbers 16, which is we have, presumably, we have 16 available slots that we can use. And the free pointer is basically indicating where the free memory begins. You can think of this pointer as a bookmark or cursor that points to the first available word. So when a program requests a dynamic memory, such as through the memory malloc in C, so the allocator simply responds by assigning the consecutive free words from this pool and then advance to the pointer forward. So after the allocation, and the memory behind the pointer is considered in use, while the memory ahead of the pointer will be remains free. So which is automatically reclaimed. So unlike the stack memory, what we have here in the stack memory is whenever we are having the function call, is creates the activation record automatically. Whenever the function finishes job, it is reclaimed by the stack. So we can still reuse that information. But here, the heap memory, if it will be persist until we explicitly freed by the program. So making its proper management will be very critical to prevent memory leaks and efficiency use of memory resources. Then coming to the question is, what is memory leak? Yes.
Basically, when you have the allocated, but you switch the pointers so that you can't play that to get that. And then I know specifically for Java, you can't really get it to that. Receive, they say you allocated a variable X, and then you pointed it somewhere else, the X is still thinking when you saw allocated.
But let's discuss about the memory leak specifically. So you have talked about the pointer itself, everything about pointer, but the word is a memory leak. What is leaking? Have you addressed why we have leak? Is the memory leak or data leak or anything is leaking? No. Any interpretation towards this? Nothing? Yes. There's not being free right. That is when you are partially getting it. It's not free right, but why is it leaking? So simply using this one as a example, I have a cup. Okay. So whenever I allocate it, So this is my memory. Whenever I allocate the memory, it means it will be used. Simply I pour water in there, right? If it's not free correctly, it's basically I'm not drinking it or anything is being like dumped over, my cup is full. Whenever getting more to this cup, more water to the cup means what? Leaks around, right? That's called memory leaks. That's the only thing you can consider of, all right? Then let's come back to here. So what we have here is clearly visualizing what we have the heap allocations. So the process of this allocations, we are starting from the left to the right. Is the left? Yes, left. Left to the right. And I was simply visualizing each scenarios consecutively. So it's a complete stories. You have to follow with me. In scenario A, our heap is entirely free. So meaning no memory has been allocated yet. So free pointer is simply placed at the very bottom. And 10 here is basically telling us how much space we have left, how many space you can allocate. If you allocate beyond that, it means you cannot pull more. Okay, pull more waters. Then coming back to our scenario B is suppose our program requests a block of memory, so that is 2. Okay, now the pointer 1 is our allocate memory pointer. So we simply point to that information area is 2, and we are simply reserved 2 blocks in the memory. And the free pointer will simply moves to here, and you have a indicating the information, how many memory blocks we have left. That's the only thing. But once I come into a question is, where is it? Here. Okay, now, can I move this pointer to here? Why not? Yes. But what is necessarily, the thing is, let's consider fundamentally, what is the necessity? We have the pointer pointing to here, and we are only allocating 2 memory address, but we are reserving actually 3. Allocation stuff. Okay, then any other comments? Okay, so let's consider the implementation wise. Why? So first, why we are allocating 3 rather than 2? Can we do 2? Yes, we can, depending on the implementation wise. If we're doing 2, it means each block we are going to sacrifice a little bit space. We're shorten it. Its memory content is the information we can hold in. It means when this space will be reserved for header. So this space basically indicating, is it a flag? Okay, it's a flag. Is it being used or not? So you have to indicating whether it's being allocated or not. Okay, then this is a header that's telling that information. If we're only allocating 2, but why are we having 3? Why are we having 3 here? Is that we can have the header information directly placed right here. Whenever we access this information, we know we have allocated 2. Then consecutive 2 memory slots is being allocated. We can use it. That's the idea. So simply is we have a header idea telling you that we have reserved 2 slots, rather than you have to simply go to the check. Is it being allocated? Is it being allocated? Is it being allocated? So that is a consecutive if statement. If we were only having 1 access right here, simply we go, this is 2 slot. I can use a while loop or for loop to do that. So everything in that range is usable. Then coming to my second question is, can I use my pointer to PTR1 here? Can I do that? Yes, we can, depending on the implementation. Okay, Yes, we can, depending on the implementation. Is that in the implementation wise, if we are accessing this information, the header information right here, we know it's header 2, okay? A header 2. It means we can directly using a for loop, right? For loop while for I is equal to 0 and less equal to 2 or something to access the entire block. But if we are moving the pointer here, it means whenever we accessing some kind of header loop, header informations, it having some content 7 right here, it means we are reaching to the end. So in this sense, in this implementation, we're simply using a while loop, simply checking one condition. Is it the header? It is not header, it is in my allocated space. If it's in the header, it means we are reaching to the end. It's simply acting as an EOP, okay, end of a program. Now, getting those ideas correct, then we come into the next scenario, C, right here, C. So in this C, we're simply having another memory allocation request, and this is the second allocation occupies the 3 words. So 3, 1, 2, 3, 3 words being allocated for pointer 2, and we're simply moving the free pointer to the next available slots. Okay? Oh, it's 17 already. So let's stop right here, and we can continue this lecture on Monday. So thank you for coming, for whoever is attending on the Zoom. Bye.